let's look at two examples of specific source charges generating electric fields and the equipotential lines that would be associated with them to get a better feel and understanding for these voltage lines. Well, of course, we are going to be utilizing delta U equals Q delta V once we have these delta V lines in there, because if I release a particle at a voltage line and it goes from high voltage, if it's a positive Q, it goes from high voltage to low voltage, that will correspond to a delta U. So I can actually use the values of those delta V lines, right, to calculate delta U's. But to understand the characteristics and the maps that we're looking at, we will go back to delta V equals ED. So in this case, the electric field is not constant. So strictly speaking, we can't just use delta V equals ED to calculate the values. We would have to use our delta U equals Q delta V to numerically solve the problem. But we know for a source charge point particle that the electric field, right, equals KQ on R squared, R hat. So that's why they point radially out. So all of these black electric field lines point radially out. And the field weakens according to the 1 on R squared. So remember, we said we need, and that's that delta V, so make sure that you have this in there. The delta V, do not lose sight of this. Delta V must be the same between the dashed voltage lines. So for example, down here, if C is at positive 100 volts, then we get a decrease in voltage as we move outward to positive 80 volts, and if it's a 20 volt voltage difference, then A has to be positive 60 volts. You would put a positive test charge down and think about its movement along the electric field line, and keep in mind that those positive test charge moves from high voltage to low voltage to identify the high and low voltage parts of the graph if you were not given that. Remember, electric field lines are always drawn by convention to push positive charges and pull backwards against the negative charges. Well, of course, these voltage lines are arbitrary because it's only the delta V that has physical meaning, just like only the change in potential energy has physical meaning. The only thing that has physical meaning is the change in voltage. So if we were told to make the point C negative 20 volts, that's okay as long as we're losing voltage. We're dropping. We're getting smaller. Negative 40 when we get to B, there's a 20 volt voltage drop, and we would get another 20 volt voltage drop, negative 60 at A. So working with the negatives can be, I know, a little bit of a pain because you have to constantly recalibrate your mind that those bigger looking numbers, 40 is actually smaller because it's on the negative number line. Well, the electric dipole, for the electric dipole, the equipotential lines are these red dashed lines. And to put in the red dashed lines, what you are going to do is focus on what we talked about. So if you weren't given the red dashed lines and you were told to put them in, what you will focus on is that the equipotential lines will always be perpendicular to the field lines. So you're just going to go in here and go to each of the fields and put in little perpendicular dashes and then connect the dots to get an estimate. And then, of course, you would have to look at your field lines as to where your field lines are further apart. We have a weaker field where the field lines are closer together. We have a stronger field. So, of course, our delta V equals ED still applies. So the smaller the D, the stronger the E to get the same delta V between those lines. So it's just a qualitative look at our equipotential lines for these two simple point particle systems, but hopefully this gives us a better understanding of how to visualize what these lines are giving us or how to draw them in if we were asked to do so.